Before diving into the Fast Fourier Transform or FFT, let's briefly look at its historical roots. In the early 19th century, Joseph Fourier discovered something remarkable. He showed that many complex physical phenomena, especially heat conduction, can be represented as a sum of sinusoidal waves. In other words, any complex signal can be decomposed into simpler sinusoidal components. This idea later became the mathematical foundation of the Fourier transform. When signals are digital, this concept appears as the Discrete Fourier Transform or DFT. However, there was a major challenge. Computing the DFT directly required a very large number of calculations. Then, in 1965, James Cooley and John Tukey introduced a breakthrough algorithm that dramatically reduced this computational cost. This algorithm is called the Fast Fourier Transform or FFT. Today, FFT is one of the most important algorithms in digital science, and it plays a critical role in many fields, including optics, photonics, signal processing, machine learning. In this video, we will not just use the FFT, we will understand how it works and why it is so efficient. You are already familiar with the continuous Fourier transform, which is shown on the slide. It describes how a continuous signal can be represented in terms of its frequency components. However, in computers, we do not work with continuous signals. Instead, we deal with discrete signals, a finite number of samples, and numerical computation. Because of this, we use the Discrete Fourier Transform or DFT. Suppose we have n samples of a signal. The formula for the DFT is shown on the slide. Conceptually, it performs the same type of transformation as the continuous Fourier transform, but with three important differences. The integral becomes a summation, the signal becomes discrete instead of continuous, and the frequencies become discrete and finite. So the DFT converts a signal from the time domain to the frequency domain. Now, there is another very interesting way to look at the DFT. From a linear algebra perspective, we can write it as x equal fnx, where fn is the Fourier matrix. This viewpoint is very important because later we will see that the FFT can actually be interpreted as a structured factorization of this matrix. We will explore this interpretation in more detail in the upcoming videos. Now the important question is, what is the computational cost of computing the DFT directly? If we look at the formula for the DFT, each output value xk requires about n multiplications and additions. And since we must compute n different outputs, the total number of operations grows roughly as n times n equal n squared. Therefore, the computational complexity of the direct DFT is O(n) squared. For small signals, this is manageable, but in large-scale simulations, especially in optics and photonics, the grid size may reach millions of points. In those cases, this computational cost becomes extremely large and often impractical. So this leads to a very important question. Can we compute the same result in a smarter and more efficient way? And this question is exactly what leads to the Fast Fourier Transform. The core idea behind the Fast Fourier Transform is divide and conquer. To understand this idea, let us assume that the number of samples, n, is even. Instead of computing the DFT of the entire sequence at once, we split the sequence into two parts: the even index samples and the odd index samples. This decomposition is shown in the formulas on the slide. Using a simple property of the complex exponential terms, the original DFT expression can be separated into two smaller summations. One summation corresponds to the even samples, and the other corresponds to the odd samples. As a result, the original transform can be expressed in terms of two smaller DFTs. We denote these two transforms as the DFT of the even samples and the DFT of the odd samples. Then the final result is obtained by combining these two smaller transforms, using the Twiddle factors shown on the slide. So instead of computing one DFT of size n, we compute two DFTs of size n/2 followed by a symbol combination. So instead of computing one DFT of size n, we compute two DFTs of size n/2 followed by a simple combination step. And this process can be repeated recursively. By repeatedly splitting the problem into smaller transforms, the computational complexity is dramatically reduced. Instead of O(n) squared, the complexity becomes approximately O log n. This recursive divide and conquer structure is the fundamental idea behind the fast Fourier transform. The butterfly is the fundamental computational block. Given inputs A and B, it produces output A plus WB and A minus WB, where W is e to the power of minus I 2 pi k over n. This structure exploits symmetry, eliminates redundant computations, enables recursive decomposition. Now, let us look at a concrete example to better understand how the FFT works. Here, we consider a signal with 8 samples, shown at the top of the slide. Since n equal to 8, the FFT algorithm first applies the divide and conquer strategy. In the first step, we split the sequence into two parts, the even index samples and the odd index samples. You can see two sequences on the slide. Next, instead of computing the full 8-point DFT, we compute two smaller transforms. One transform corresponds to the even samples, which we denote by EK. The other transform corresponds to the odd samples, which we denote by OK. On the slide, you can see the complete calculation of these two 4-point DFTs. So after this step, we have obtained the values of EK and OK. These two smaller transforms will now be combined in the next step to produce the final FFT result. Now we move to the final stage of the FFT computation. At this point, we already know the results of the two 4-point DFTs, EK and OK. To obtain the final 8-point FFT, we combine these two transforms using the Twiddle factors. The Twiddle factor is defined as shown on the slide, and it provides the complex exponential weights needed for the combination. Using the FFT combination formulas, we compute the values of xk and xk plus 4 for the different values of k. All of the intermediate calculations are shown step by step on the slide. After performing these combinations, we obtain the final FFT result, which is the vector x. This example illustrates the central idea of the FFT. Instead of computing a single 8-point DFT directly, the FFT algorithm computes two 4-point DFTs and then combines them using Twiddle factors and butterfly operations. As a result, the computational complexity is reduced from O(n) squared to O log n. And this dramatic reduction in computational cost is what makes the fast Fourier transform such a powerful algorithm. Now, let's look at why this efficiency matters so much in engineering applications, particularly within the fields of optics and photonics. The FFT isn't a tool, it's the engine behind some of our most critical simulations. For instance, optical wave propagation. When we calculate Fresnel and Fraunhofer diffraction integrals, the FFT is what allows us to model how light moves through space. Diffraction simulation. We use it to find the Fourier transform of the optical field, specifically at the focal plane of a lens. Advanced numerical methods. Whether we are performing spatial filtering, finding numerical solutions to the Maxwell equation, or using spectral methods to solve complex PDEs, the FFT is what makes these large-scale computations feasible. But the reach of the FFT extends even further into modern frontiers like machine learning and physics-informed neural networks. Here, the FFT is used for spectral bias analysis, understanding which frequencies the network learns first, frequency domain feature extraction, helping models see patterns that aren't obvious in the spatial domain, solving PDEs, accelerating the training of pins by working in the frequency domain, and denoising, stripping away noise to reveal the underlying physics. In short, the FFT provides the essential insight into the spectral structure of our solutions, making it an indispensable part of the modern engineering toolkit. Now, let's get into the complexity analysis to see exactly why the FFT is so much faster. When we analyze an algorithm, we don't measure time in seconds because hardware varies. Instead, we define a function, Tn, which represents the number of basic computational operations required for a problem of size n. In the standard radix 2 FFT, we use a divide and conquer approach. We take a sequence of size n and split it into 2 halves. This means a problem of size n is broken down into 2 subproblems of size n over 2, plus a combination step which we call the butterfly stage that requires roughly n operations. This gives us the famous recurrence relation, Tn equal to 2 Tn over 2 plus n. If we solve this relation, we arrive at the well-known result 𝑁log 𝑁. This means the running time grows almost linearly with the data size, just with a logarithmic factor. To put that into perspective, if we stayed with the direct DFT, our complexity would be 𝑂n squared. Why? Because we have n outputs, and for every single one, we have to sum over n terms. As n grows into the thousands or millions, the gap between n squared and 𝑁log 𝑁 becomes dramatic. It's the difference between a simulation taking a few seconds versus several days. Now, as powerful as the Fast Fourier Transform is, it isn't always the right tool for the job. There are specific scenarios where using the FFT might actually be overkill or even technically incorrect. First, let's consider very small n. If your signal has only a handful of samples, say 8 or 16, the overhead of setting up an FFT algorithm might outweigh its benefits. In these cases, a simple direct DFT is perfectly fine and sometimes even faster. Second, we have non-uniform sampling. The standard FFT algorithm strictly requires your data points to be equally spaced in time or space. If your sensor data is jittered or sampled at irregular intervals, a standard FFT will produce artifacts. You would instead need a non-uniform FFT, NUFFT, or a different spectral analysis tool altogether. Finally, what if you only need a few specific frequency components? If you're only interested in 1 or 2 known frequencies, for example, detecting a specific pilot tone in a communication signal, it is much more efficient to use the Gortzel algorithm or a direct computation rather than calculating the entire spectrum with an FFT. So, while the FFT is our workhorse, always remember, for very small datasets, irregular grids, or targeted frequency analysis, alternative methods are often more practical. To wrap things up, let's recap what we've covered today. We started by defining what the DFT is, our mathematical bridge between the continuous world and the digital one. But we quickly saw its limitation, a computational complexity of 𝑂n squared, which makes direct calculation impossible for large-scale data. We then explored how the Fast Fourier Transform changed the game, reducing the complexity down to 𝑂nlog 𝑁. This isn't just a faster version of the same math, it's a brilliant, structured reorganization based on the recursive divide and conquer strategy. We looked at the butterfly structure, which is the fundamental building block of this efficiency. And finally, we discussed why this is so critical in fields like optics and photonics, where the FFT makes simulating light propagation and solving Maxwell's equations actually feasible in a reasonable amount of time. The big takeaway today is this. The FFT is more than just an algorithm. It is a masterclass in mathematical reorganization, proving that how we structure our calculation is just as important as the equations themselves. Thank you so much for watching. I hope this deep dive into the FFT and its engineering applications was helpful. If you want to explore more about how mathematics fuel modern engineering, make sure to subscribe to our YouTube channel and hit the notification bell. For more in-depth tutorials, technical articles, and resources, don't forget to visit our website. We have a lot more exciting content coming your way. See you in the next video.